Characterization 3 of Pascal's triangle has to do with symmetry, or now you have it, now you don't. An example here is that 9 choose 2 and 9 choose 7 are going to be equal. This is in the 9th row, the second position. Remember, it starts with position 0, position 1, position 2, and position 7 are both 36. In general, n choose r is equal to n choose n minus r. Now, why is this? Let's go back to the 9 choose 2 and the 9 choose 7. If we want subsets of size 2, we can do that. We can take a look at our 9 elements and pick out 2 at a time. And the number of ways we can do that is 9 choose 2. Well, to find subsets of size 7, we could pick out elements, picking out 7 at a time, or we could decide what is not going to be in the set. So we could pick 2 elements and say they're not going to be in the subset, and the remaining 7 would be in the subset. So for every subset of size 2, there's going to be a subset of size 7. It's a matter of using the elements in your subset or not using the elements in your subset. Characterization 4. The total of row n equals the total number of subsets from a set of size n, which is equal to 2 to the n. So let's take an example of n equals 5. We have in the 5th row 1, 5, 10, 10, 5, and 1, which looks like 32. And in fact, that is 2 to the 5th power. In general, n choose 0 plus n choose 1 plus n choose 2 plus and so on up through n choose n is equal to 2 to the n. Now, why is this the case? Well, first of all, we do know that the row is a complete list of all the subsets. In this first case, we have the subset that is the empty set. We choose 0, and the empty set is a subset. Doesn't have anything in it, but it is qualifying as a subset. And in the last position, n choose n, we have the entire set. We had 5 elements and we chose all 5 and made a subset. Those are kind of the uninteresting extreme examples. And here we have the subsets of more interesting size 1, size 2, size 3, and size 4. Now, why is it that this is 2 to the n? The reason it's 2 to the n is because every element that's in our original set, let's say we have A, B, C, D, E, every element in our original set is either in the subset or not in the subset. So we've got 2 choices for the letter A, in or out. 2 choices for element B, in or out. 2 choices for C, 2 for D, and 2 for E. So we have 2 to the 5th. Characterization 5 is the hockey stick principle. The hockey stick principle, you start on an edge here and just come down as far as you want. I've come down here 6 elements. And then you take a little curve. And the hockey stick here, this is the handle of the hockey stick, and this is the blade of the hockey stick. Here's another example, the handle of the hockey stick and the blade of the hockey stick. The hockey stick principle says that all the numbers in the handle of the hockey stick add up to the number that is in the blade. So 20 plus 10 plus 4 plus 1 adds up to 35. This is actually a direct result of the characterization that says in order to get any particular position, for example this 21, it's the sum of 15 and 6. This 21 can also be found by adding 15, 5, and 1 in the handle of the hockey stick. Characterization 6 is kind of a simple characterization. The only reason I put it in here was to establish a pattern. Characterization 6 says that the first diagonal are the stick numbers. Don't be alarmed that this is super simple. So this 1, it's a stick of length 1. This 2 is a stick of length 2, stick of length 3, and so on. The only reason we do this boring lead-in is so that we can do characterization 7, that the second diagonal are the triangular numbers 1, 3, 6, 10, 15, 21, which we talked about in the previous video. Now the question is, why, for example, is 10 a triangular number? You might pause the video and see if you can figure that out. The reason 10 is a triangular number is the hockey stick principle. 10 is the sum of the numbers 1, 2, 3, and 4, which is the sum of sticks. If you sum up sticks, you get a triangle. Now that we have the triangular numbers, we're going to apply that and the hockey stick number to add up the triangular numbers. And we get the tetrahedral numbers. The characterization number 8 is that the third diagonal are the tetrahedral numbers, using the same logic of the hockey stick principle. So for example, if we take these first 4 triangular numbers, 1, 3, 6, and 10, and stack those up, we get the tetrahedral number 20. We see that the first 4 tetrahedral numbers are 1, 4, 10, and 20. And here is a 3D picture of them, 1, 4, 10, and 20. And hopefully you can see the triangular numbers being added up. Now, how does this relate to the 12 Days of Christmas song? Well, the top of our tetrahedron is on the first day of Christmas, my true love gave to me a partridge in a pear tree. On the second day of Christmas, my true love gave to me 2 turtle doves and a partridge in a pear tree. Third day, 3 plus 2 plus 1. Fourth day, 4, 3, 2, 1. Fifth day, 5 golden rings, 4, 3, 2, 1. So what we want to find the number of gifts in the 12 Days of Christmas song is to find the 12th tetrahedral number. Let's take a look at our Pascal's triangle. Let's see where the 12th tetrahedral number would be. Get the correct diagonal here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 364 is the number of gifts in the 12 Days of Christmas song. In the next video, I'm going to be talking a little bit more about tetrahedral numbers and going on to additional characterizations of Pascal's triangle.